Welcome back to Unwrapped. I'm Mark Summers, hitting the big screen to find out which snacks are now showing in America's movie theaters. How about one of the most popular candy items in the nation's top 3 theater chains? That would be Twizzlers. Let's watch. So maybe that blockbuster movie lacked a few twists and turns, but here's one snack that doesn't.
Twizzlers has been a movie theater favorite all the way back since 1930 when it was first introduced. And really, it's a great treat at the movies. It's something that you can share. It's something that you can snack on throughout the movie. It doesn't melt.
Snackers seem to agree. Every year, they chew through more than 1 million miles of Twizzlers.
That's enough to go around the world 40 times.
At the Twizzler factory in Lancaster, Pennsylvania, candy makers have their hands full meeting such a demand.
Primary ingredients used are flour, liquid sugar, corn syrup, and water.
Those combined ingredients or slurry mix for an hour in huge tanks. The slurry then gets pumped overhead and into cooking kettles.
Shortening, coloring, and flavor are added, and then the liquid mass is cooked and agitated for approximately 4 hours.
Finally, the red licorice is thick enough to twist and shape. It's shot through several turning nozzles and onto giant boards. You could say this is where the Twizzler gets its twizzle.
One secret that no one ever knows about Twizzlers, there's a twist in every inch, about 8 to a piece. And a product is cut to the various lengths for the different sizes and shapes of Twizzler products that we make.
Once cut, boards of Twizzlers slide onto giant carts and head to the drying tunnels. After 10 hours behind these big metal doors, the Twizzlers are ready for packaging.
We have both robotic and manual packaging and scanning here at our plant.
Whether by machine or by hand, there's not a Twizzler out of place. They're carefully wrapped in those popular 1-pound bags.
The Pounder's the best pack, 16 ounce. That's a single serving. That's what we like to think.
Over the years, Hershey's has gotten creative with these twisty little candies. They now come in 20 different shapes and flavors.
My favorite Twizzler is the chocolate Twizzler, but I've been known to munch on my fair share of strawberry Twizzlers too.
The most popular is the strawberry, of course. And the newest on the line, a rainbow twist.
6 flavors, 6 colors, all in one bag.
Twizzlers are a great treat. They're chewy, they're fun. We like to say they make mouths happy.
Hi everybody, welcome to Unwrapped. I'm Mark Summers, and today we are taking a bite out of our favorite peanut butter treats at a very convenient location. And this is usually where you will find the classic combination of peanut butter and chocolate known as Reese's. So let's head to the Hershey factory to watch them creating these famous cups.
Peanut butter and chocolate. It's one of the most famous candy combinations. But did you know the creator of this cup actually worked for Milton Hershey?
H.B. Reese, who founded the Reese's Peanut Butter Cup, was a dairy farmer here in central Pennsylvania.
In the early 1900s, Harry Reese supplied milk to make Hershey's chocolate. He was so inspired by Milton Hershey, Reese decided to try his hand at his own chocolate company.
He started to make candy and had some different products. But when he stumbled across and made the first peanut butter cup, it was the only one that mattered anymore, and he went down to just a one candy business.
Reese built his own factory a few blocks from the Hershey plant. Now it was Hershey's turn to supply Reese with chocolate for his peanut butter cups. A few decades later, Hershey bought Reese's Candy Company.
People love Reese's Peanut Butter Cups. As a matter of fact, it's the #1 selling candy bar for the Hershey Company, but it's also the #1 selling candy bar in the United States and Canada overall.
The process begins with a bag of peanuts, but these are no ordinary bags.
Each super sack contains 2,500 pounds, which is roughly almost 2 million peanuts per super sack.
Truckloads of nuts come into the plant from 3 states.
Our peanuts are sourced from the southeast United States, Alabama, Georgia, and Florida.
The peanuts get cleaned, sorted, and roasted.
We roast roughly 200 million peanuts on a day.
After the nuts go through a grinder, the creamy peanut butter glacier slowly crawls toward the chocolate. The chocolate has to temper before it's ready.
The tempering process for our chocolate involves a heating and a cooling cycle. The heating cycle allows it to be liquid when we need to apply it to our peanut butter cups. The cooling part allows it the ability to set up.
But first, we need a wrapper.
Here we make all the paper cups that are used to hold our Reese's peanut butter cups for this particular plant.
Miles and miles of paper feed through a machine that stamps the cup shape into the paper in 5 different sizes.
We apply heat to actually set the shape of the cup. This particular area produces roughly 30 million cups on a daily basis.
Now we're ready to fill the cups.
We deposit chocolate into the mold. Then we put what we call a peanut butter plug. We extrude that into the cup.
The plug is a solid chunk of peanut butter. The cups ride over vibrating belts to get the peanut butter to spread out.
The vibration of the peanut butter plug is important. We need to smooth it out so it's nice and flat.
Next up, a depositor squirts the final chocolate layer into the cup. A puff of air spreads out the chocolate. Then the cups cool for 30 minutes before they're wrapped up and shipped across the globe. And get this, Reese's makes enough peanut butter cups in 1 year to circle the earth 7 times.
If you were to melt down the number of peanut butter cups that were sold in 2007, you would have enough melted chocolate and peanut butter to fill a football field in 65 feet depth of chocolate and peanut butter.
Now that's a peanut butter pool that would make Harry Reese proud.
Good morning, everybody. My name is Lou Felice. I'm a chemical engineer by degree, and I work for Hershey, if you couldn't tell by all the treats and publicity there. So really, first thing I want to do is thank my employer, Hershey Foods, for letting me come here and talk to you guys today. But I'm also a member of the AICHE, which is the American Institute of Chemical Engineers, and it's a professional society for chemical engineering professionals, and every engineering function has their own society, but we have a local section here, and we do a lot of educational outreach, coming out and speaking to students. So actually I kind of wear both hats today, representing Hershey and the AICHE to come and talk about chemical engineering. So I've been working for Hershey for 25 years. It's a long time. Done a lot of different jobs, worked in research and development, developing the manufacturing processes for new products. I've worked as a plant engineer, just supporting manufacturing, doing projects and troubleshooting in the plant. I've worked in corporate engineering, design engineering, and also in operations technology. That's where I work now. I have my chemical engineering degree from Drexel University, which is in Philadelphia. So that's just a little bit about me. And so what I'm going to do today is give you an overview of chemical engineering. So topics I'm going to cover: what is a chemical engineer, roles of a chemical engineer, salary comparisons, which everybody's always interested in, traits of an engineer, in pursuit of a degree, what does it take, and then we'll have time for questions if I don't speak too long. So before I start, though, let me see a show of hands. How many are freshmen? Any freshmen in the room? So we have a couple. Sophomores? Okay. Juniors? Seniors? 4 seniors. So the seniors, are you guys already accepted into a college somewhere? Yeah. Yeah? As a chemical engineer, or are you still undecided? Where are you going? Penn State. Okay, how about you guys?
University of Boulder, just undeclared engineering.
Okay.
I'm going into the Navy.
Okay. Are you ROTC program or
No,
into the Navy?
full-time, or active duty, and
Okay.
nuclear physics program.
Okay.
Didn't finish flying,
Okay. So
real,
gotta get on the ball there, huh?
of course.
Yeah. Okay. Good. So I guess everyone else who's still discerning, you know, do I want to go into engineering? Do I want chemical, electrical? Hopefully this presentation will help you get a better insight into what chemical engineers do and help you decide your career path. So what do engineers do? And this is my dry sense of humor. Most engineers don't drive trains. And so what is engineering? And you can break down engineering into kind of like some vague statements that says engineering is applying scientific and mathematical principles, experience, judgment, and common sense to create things that benefit people. Engineers are problem-solving people, and when you think, when I look back on everything I do at work, I solve problems, whether it's trying to design a new product, whether it's trying to troubleshoot a process. It's all about, there's a problem and we're trying to figure out how to fix it. And usually we're either trying to make something work better, more efficiently, make it have more capacity, or make it have a process convert raw materials to finished product more in a more cost-effective manner. And we use our skills and dedication to search for better ways to solve problems. Some snippets that have been used in the past. There's Engineers Week is actually this weekend, or this weekend and next week. That's probably why this is held this week. And so some of the phrases we've used for Engineers Week: engineers turn ideas into reality, solve problems by relying on their creative and academic skills, and we undertake tomorrow's challenges today. So engineering is really an exciting career field. So what is chemical engineering? How is that different than other engineering? And if you guys ever have questions, you can just ask anytime. You don't have to wait till the end of the talk. So really you're relying on some of the foundational elements of chemical engineering, chemistry, physics, and math, to solve problems involving the production or use of chemicals and biochemicals. So what do chemical engineers do? And these are the different, I would say, job functions, and really this isn't limited to just chemical engineering. Any engineering discipline, you have these different areas that you can work. You can work in research and development, process design, process control, process optimization, project management. You can be in manufacturing, and then a lot of engineers go on to either be in management. You can be in technical sales. Some engineers go on and get a law degree. I know I have a friend he has his bachelor's in chemical engineering. He went on to get his law degree, and now he's a patent lawyer. And the one thing about engineering and chemical engineering is it gives you a very strong foundational education that you can really apply to a very diverse career field. So what I was going to do was break down each one of, or several of those different disciplines, some of the more common ones, and kind of tell you what they do. So in research and development, you're really developing, planning, and testing to get a better understanding of a technology, and that can be used to create a foundation to develop new products, to develop new manufacturing processes, or just new technologies. In research and development, a lot of times the engineers will be working either at a laboratory scale to start, and then they have to scale up, and they'll go to a pilot scale, which is a small scale replication of a manufacturing process, and then you have to be able to scale up to production. And really what you're trying to do in research and development is to develop a fundamental understanding of the topic you're researching. You're trying to really get to the basic scientific principles and engineering principles of your research, so you have a good understanding of that technology so you can apply it. So this is a photograph of, this is our pilot plant at Hershey, and this is actually a chemical engineer setting up an evaporator to do some research and development work. I can't get that. So, and I think about Hershey's and some of the things that our research and development group has done, and more recently, you guys are familiar with the Air Kisses and the Air Delight, which is the chocolate with the air bubbles in it. Well, we had a team of research engineers trying to figure out, that whole aeration technology, and they did a lot of testing like on different gases, like if you aerate with air versus carbon dioxide versus pure nitrogen, how does it impact the finished product, what type of processing parameters do you need, and how does that impact the finished product, does it affect the way it eats, the size of the air bubbles, the number of air bubbles, does it affect the shelf life, and they spent years developing that technology to the point that they had a great understanding of the technology. They were able to say, here's the best way to do it, to commercialize it the most efficient way, and turn it over to the design engineers who actually design the process, buy the equipment, get it installed in the plant, and get it operational. Make sense? So, and at Hershey, this is kind of how our workflow is. Like we might have, it's mostly on innovation, on new products, so research and development, like research and technology, and they'll take it to a point that they say, okay, we understand the principles, this is how we would recommend you do it, but it's not scaled up to any scale that can be taken to manufacturing. So then we have a process development group that would actually work in our pilot plant doing the larger scale testing to develop that technology. And really what they're doing is trying to understand, they're working at a scale that might be, say, anywhere from 10 to 1,000 times smaller than production, but they're trying to define the operating parameters at that scale, and then they can use their engineering background to do calculations to scale that process up to a full production scale. The other thing the development engineers will do is they'll start to put together the process flow, which is really like a flow diagram that shows all the raw materials coming in, the different unit operations or pieces of equipment that are used. Say, for instance, all the materials come into a tank and they're mixed, and they start to define the operating parameters. This tank has to have a jacket with 120-degree water because we have to heat the mixture up, and then we have to pump it over to an aerating machine, and we're injecting, a gas in at so many cubic feet per minute. And they start to define the process and lay it out, and then they have to start developing a preliminary capital estimate, which is how much is it going to cost to buy all this new equipment and get it installed in the plant? Because everything that we do, there's an economic basis for all the projects we work on. So, for instance, they might say, and I'm going to make these numbers up, they might say, okay, we think we can sell $10 million a year of Air Kisses. So then the engineers say, okay, well, this is the process we need. It might cost us $40 million to buy that equipment and put it in a plant. And so then the finance guys say, well, we need a certain rate of return to be, to be economically feasible. And you can go around in several iterations of that sometimes where they say, no, we need a better margin on the product. Can you reduce your capital? The engineers go back and say, okay, let me see, what can I compromise in my design? How can I design this to give the same efficiency in product but be less expensive to purchase the equipment? So the engineers have a lot of responsibility. So these are photos, mini Reese's Pieces. We sell those now when we do like, I think ice cream, I'm not sure who it is, but they mix them into ice cream and things like that, but they're really small Reese's Pieces. But this is photographs of, in our pilot plant, the development, actually I worked on this project, developing mini Reese's Pieces. And it's kind of really neat how this process works. On the top left, you see that's a tank, a mixed tank, and there's a pump at the bottom, and it pumps this peanut butter into these are horizontal cylindrical rolls. And you can see they have those little cavities in them, so each one of those cavities is half of a Reese's piece, and the rolls rotate together. And so the two halves made up, and there's a heat transfer liquid that flows inside those rolls. It's like minus 30 degrees Fahrenheit. And so the peanut butter, as you see in the top right-hand picture, is the peanut butter being pumped into the nip of the rolls as it's rotating. And this picture on the bottom is a picture of the underside of the rolls. So that's actually like a mat of Reese's Pieces centers. And the amount of time that it's in that nip is very small. It's like several seconds, but it's enough to take it from that liquid to a solid. And then we have to further cool it, and you tumble it, and you take all that webbing that's connecting the little centers together, you tumble it and screen that off, and then you have all your centers, and then they go on to another process where we put that candy coating on. So, that's the best thing about working at Hershey is like, I say it's a sweet job, but you get to eat everything you work on. It's a lot of fun. So then we have a process design group. And so the development engineers will develop a process, establish all the operating parameters, but it's done at a small scale. And then the design engineers will actually do the scale up. And they do all the detailed engineering, very detailed. They'll do a lot of calculations to calculate equipment sizing. They'll do equipment layouts, which are mechanical layouts of equipment like on a floor. They'll do process and instrumentation diagrams, and I have several copies of those up here. You can look at them if we have time at the end. And these are some of the most detailed drawings. This is a very the design phase is very detailed and time consuming. And this drawing basically shows is the blueprint of the process. It has every pipe, every pump, every piece of equipment. It has every control element. So I can look at this drawing and I can tell you what's flowing in the pipe, the size of the pipe, the material it's made of. I can tell you how it's being controlled. There's valves, and everything is labeled in a way that this is a document we leave with the plant after the equipment is installed, and it becomes a great tool for troubleshooting because, and this is just another thing that the engineers do, you know, say for instance, a pump doesn't turn on when it's supposed to turn on. Well, you have to figure out, well, why is it not turning on? You can go to this drawing and say, and all this equipment is controlled by computers, and the computers have like, you know, input-output racks, and so there's an output that would send a signal, electronic signal, to the starter for the pump. And I can go here and I can say, okay, that starter is in rack 5, output 16, so you can go to the control panel and look at rack 5, output 16, and you can see, is the light coming on sending the signal? So why is the pump not running? Is it because it's not getting the electrical signal? There's something wrong with the program, something wrong with the electrical hardware? Or is it sending a signal and maybe there's something wrong, the starter is bad, or it could be a mechanical problem. Maybe the motor's burned out, or maybe the pump is seized up, and it's a mechanical problem. So these drawings allow the engineers to kind of troubleshoot more efficiently because it can tell them where to look to diagnose the problems. So they'll put together this process and instrumentation diagram, and then from here they can develop an equipment list that lays out, here's all the equipment I need to buy, and then they can start writing specifications for each piece of equipment, and they send them out to vendors, and they get quotes, and they put together the whole package to go out and purchase and install the equipment. And also material and energy balances. We always do what's called material and energy balances, which is balancing the material flow, all the materials coming in. They all have to go out and go somewhere and be accounted for. So for instance, when you're roasting peanuts, say we use, you know, like 200 million pounds. I think we're the largest, believe it or not, we're the largest peanut consumer in the United States. We use like 200 million pounds a year. And you buy peanuts, they're usually like 6-8% moisture. And we roast them to develop the flavor before we convert them into peanut butter. But when you roast them, you lose moisture. They come out around 1%. So as a chemical engineer, you do these flow balances because you need to make sure you're bringing in enough peanuts to supply your peanut butter lines because you're losing moisture. So we account for all the mass in the process. We do the same thing with energy. We account for all the energy, because if we have to heat something, we need to figure out, okay, we need steam to heat that, how much steam do we need? So there's a lot of tedious calculations that go into the design phase. And so if you're not a really detail-oriented person, you don't want a design engineering job. So that's a P&ID. That's actually a caramel evaporator right there. That's how we make caramel. We'll batch up all the raw ingredients, we heat it up, we pump it through this evaporator, which will evaporate the water, take it to the right solids, then it goes on to the process. Process optimization. So this is another area that chemical engineers work. This is currently the department I'm in. So we really focus on all our existing manufacturing processes, and we try to come up with ways that we can make them run more efficiently, produce less waste. How can we improve the capacity without buying like a whole new line? And we get calls a lot of times from the different people in the company saying, you know, we're doing our planning, it looks like we're going to be out of capacity on this item. You know, we know it's going to cost us, say, $30 million to put in another new line, and we want to delay that spending. If you guys can figure out how to get us 15% capacity without spending a lot of money, we might be okay for another 2 years. And so we'll send a team or send an engineer out, and they'll study the process, and you know they'll look at it and talk to the operators and get a good understanding, and then come up with ideas and maybe do some testing to see whether they can improve the capacity. Automation is another area. You know, you can reduce your operational costs by reducing labor. So if there was like an operation that's kind of manually labor intensive, you might be able to automate that. So that's another area. We do a little bit of that, not a whole lot as a chemical engineer. And then just process and product troubleshooting. A lot of times, you know, we're making products from agricultural materials. So everything that we're using as raw ingredients are being grown agriculturally, and they're never the same. You know, if you think about a Hershey milk chocolate bar is made from milk from a cow. And the milk from a cow, the composition of that milk changes as the seasons go on, because it depends on what the cows are eating. And in the winter, the cow's milk has a different chemical composition. The fat content is different, and so there's seasonal fluctuations. The same thing with peanuts, with almonds, with you know, they vary as year to year they vary, and throughout a season they vary. And so we have to compensate for that in our processes. And so a lot of times we'll get calls from the plant saying, you know, there's just something isn't working right, we're not running, you know, we had to slow the line down, we can't get it to work right, and we'll go investigate, and you know, some of the times it actually goes back to the raw materials and this fluctuation in the commodities that come in. This is a project I worked on several years ago, Cookie and Cream Kisses. So when we make Hershey Kisses, there's two ways we make them. One is the drop deposit method, like we make our solid kisses. If you've ever been in the chocolate world, you see they get deposited on the belt. The other way we make them is we mold them in molds. And when we make cookie and cream, we actually mix the cookies and the chocolate, and they go into this depositor. And this is a plastic mold which has the shape of the kiss in it. 360 kisses in a mold. And this line was initially purchased to make hugs and hugs with almond and kisses with almond. And it wasn't really designed to make cookie and cream. So when marketing wanted to introduce cookie and cream, you know, they said, well, the engineers started looking, where can we make it? We can put it on this line. The problem was when they put it on this line, because of the cookie pieces and the way this depositor is made, they could only deposit into half of the mold. So the capacity of the line got cut in half, which means now the cost to manufacture that product goes up, because you're only making half the amount of product for a given period of time for the labor complement. And so they were okay running like that when they first introduced it, but then they wanted to start selling more of it. And they wanted the product to be more financially attractive. So they said, well, what do we need to do to get this, up to standard output compared to all the other products that it runs? And so the first thing we do is we call the vendor. We call the equipment company that, we bought this line from, and we say, well, we'd like to, get back to running X pounds a shift like we normally do. And I say, okay, well, because we can only get 180 with this depositor, you need to put in another depositor. You need to reconfigure the line. It's going to cost you $1.5 million to do that. And we're like, no, we don't want to spend $1.5 million. And we say, okay, well, maybe we can change the design of some of those parts so that it can work, on 360. And so I worked with the mechanics, and we studied it. We did some tests. We did some revisions of design, and this becomes more like a mechanical engineering project, but like all the engineering disciplines are somewhat interrelated, and you get a good foundation on all of them anyway. And so we came up with it took us 6 months. We had to make several iterations where we designed some of these plates on the bottom of the depositor to get like really streamlined flow, but we eventually got it to the point where we could do a whole mold deposit and get the line up to full speed. And it cost us like $10,000. So rather than spend $1.5 million, because that's what the equipment vendor, they always want to sell you equipment, and we came up with our own solution. So that's just an example of some of the projects that we work on. So now transitioning to placement by job type. So this is for chemical engineering, all the different types of, and I think this slide I don't have a date on it, so it's a little old, I think, but you can see like 24% of chemical engineers go into the chemical industry, 10% go into biotech, 6% go into design and construction. There's companies out there that all they are is a company of engineers, and they sell their engineering services to other companies to do their design and construction work for them. So these are like, when you think about chemical engineering, these are like the areas that you could get a job. Food industry, 11%. Electronics industry, 17%. People wouldn't think, a lot of people intuitively don't think that there's chemical engineers in the electronics industry, but there is, because when they're making those printed circuit boards, there's a lot of chemical engineering technology in the back-end manufacturing of the components. So fuels, 17%, is probably fuels, environmental, and biotech are growing areas. Pharmaceuticals not on there. I guess maybe that's lumped into biotech. And a lot of people don't, they don't think food companies would have chemical engineers. But why do you think food companies hire chemical engineers? Anyone have an idea? Yeah.
Give the food better shelf life.
Right.
Well, there's chemicals in food.
That's right. Food, all food is a chemical. A lot of it's organic chemicals, and some are inorganic. But so these are just examples of local companies that hire chemical engineers. You're probably familiar with some of them. Armstrong, they make like floor tiles and ceiling tiles and all different types of materials like that. 3 Mile Island. Gladfelter is a paper company, and you can tell this is an old slide because Tyco. That's right, Tyco. They make electronic connectors and different types of electronic components. So, show me the money. This is everyone's favorite information. So this is from 2010 salary survey. This is the top 5 starting salaries of any 4-year degree in college. Any 4-year degree, any bachelor's degree. And what are the top 4 of the top 5 are what? Engineers. Petroleum engineer is a very specialized area of chemical engineering. But chemical is right up there. So one of the reasons that some people go into chemical engineering, it's very highly compensated. These are median salaries by function. So this is from a 2009 American Institute of Chemical Engineering Employment and Salary Survey. And the reason these numbers are so high is because these numbers come from a population of engineers of like all ages, of all years of service. And the median is just the value that's right in the middle of all their responses, right? It's not the mean or the average. And so you can see big numbers here, and all the different types of engineering jobs. So I'm not going to go through all those, but I just thought it's interesting to see that. And then this is from 2009, median salaries by years of experience. And so what you can see is from less than 6 all the way up to 26 to 30 years, there's very good growth in your salary. So the more experience you have, the more valuable you are, the more highly compensated you are. So, what should I be when I grow up? It's chemical engineering for me. So, the key disciplines from an educational perspective are math and statistics, physics, computer science. Your core subjects really are chemistry and in college and is transport kinetics. So you start studying things like fluid mechanics, mass transfer, heat transfer, all these kinetics. You guys have had physics, right? Some of you? Who's had physics? So you guys have already had like heat transfer and probably no fluid dynamics. Electricity and magnetism, maybe. So how do you know whether chemical engineering is for you? So some of the best ways are doing what you're doing today. Go out and listen to people talk about the career field. Try to get a job shadow. There's a lot of companies that will offer job shadows. Read about chemical engineering on the internet. There's more information out there than you could ever comprehend in a given period of time. You can take tours of companies, of manufacturing facilities, to see processes. So high school preparation, good study habits, communication skills, math, chemistry and physics, and AP classes. So in college, the curriculum is very intense, and you need a good foundation in all these core fundamental areas, math, physics. You're going to take more math than you ever would want to take, and that's really true of any engineering degree. The chemistry, a lot of chemistry, that's what really differentiates you from the other engineers. And then in high school, AP classes are really good because they're a great way to get some college credits at a very low cost before you get into college. So I know students who, very high achievers, but they go into their first year of college with like 20 credits and they can skip a whole semester. So what is college like? It is very hard. You will spend more time studying in college than you ever have spent in your life. You'll have friends who are non-engineering majors, and they're going to be going out to the frat parties. They're going to be going out to watch the football games, and they're going to be going out having a good time. You're going to be in your room studying, doing homework. So it's hard. There's a high degree of difficulty. The subject matter is very theoretical, and it's very hard. It's not easy. The first 2 years in college, most colleges now, you don't need to specify a discipline. It's just like general engineering, and you all take pretty much the same classes. You build your foundation. And what's really important is to do really well in those first 2 years, because it's like building blocks. And the better you do in those first 2 years, the better you'll do in your last 2 years, because you're going to use what you've learned as a freshman and a sophomore in the classes you take as a junior and senior. And I can't stress that enough. So we kind of hit on some of those core topics. And then the other thing that's really important is summer internships and co-op programs. Are you guys familiar with that? Summer internships or co-op programs? You heard of that? Some schools, you're actually required to do a co-op, like Northeastern, University of Toledo, Drexel. It's pretty much a mandatory program. I would highly, highly, highly recommend you go into a co-op program. There's so many advantages to going into a co-op program. At Hershey, I started my career at Hershey as a co-op student. And basically, I went to Drexel, so that's a 5-year program. and you go to school. Your first year, you do your freshman year, you're in school, and then the next 3 years, you work for 6 months, and you go to school for 6 months, and you alternate. And you work in a company as kind of like an engineering apprentice. You're working with other engineers. And the benefits of that are you're getting valuable experience that 90% of the other undergraduate students aren't getting. You're going to be able to put that on your resume, and when you're looking for a job, you're going to be standing out above everybody else. You're going to be making contacts with a company or multiple companies that could potentially be your future employer, as it worked out for me. You know, I did a really good job as a co-op. The company liked me. I loved the work. I loved the company, and they hired me when I got out of school. So the pay. We have 3 co-op students year-round in my department. They're either chemical or food process engineers. How much do you think I pay these guys an hour? Any guess? Huh? Nothing. These guys get paid anywhere between $17 and $20 an hour to work for me. Now, what would you rather do? You know, what are your summer job options if you're not in a co-op or a summer internship? You can work at McDonald's for $8 an hour, whatever minimum wage is, or you can work for a company doing real engineering work.
That's good.
And the other thing is, you're working in your potential career field, so you're finding out, do I really like this? I had a co-op student come to work for me, his first co-op rotation. When he left, he went back to school and he switched his major to civil engineering because he said, I don't like that work, I'm getting out. And it's better he found out then than after he spent, you know, $120,000 or $150,000 on an education, got this degree, got out in the workforce, and found out he didn't like his job. So, I mean, hands down, I would do a co-op, many benefits. And if you think about, well, it's going to take me an extra year, that's no big deal. I mean, the benefits of all that experience, and you're going to make good money doing that work. So, selecting a college, you guys probably have already been talked to about what to look for when you're selecting a college. So I'm going to skip that slide. Pros and cons of engineering. Pros: high salary, good placement, diversity of industries, advancement is good, and engineering is a respected profession. The cons: well, it's hard work. There is some cyclical job demand. There's travel, which, you know, depending on where you're at in your life, and some people don't mind the travel. At Hershey, most of our engineers, like our corporate engineers, we work out of the Hershey office, and our plants are all over the world. So when we do projects, we go to the plants, we do a project. When we built the plant in China, we had 2 guys. They would go for like 2 months, come back for 2 weeks. Go over for 2 months, come back for 2 weeks. They did that for like a year and a half. Now, if you're young and you don't have a family, boy, is that an exciting opportunity to go live in China. We even had a guy, we put him over there for 3 years as the plant engineer once the plant was built. He was a young guy. He was actually married too. He took his wife, and they lived there for 3 years. And you know, he got very well compensated for that. He didn't have to pay for his housing or anything. Great opportunity. Now, if you're once you get married and have kids and you have a family, that's when the travel can become a little tough, but a lot of people make it work and they don't mind. Job demands: you won't find many engineers who are working 40 hours a week and you don't get paid overtime. Most engineers are probably working 50, 60 hours a week. I mean, it goes up and down, but that's just the nature of the work. So these are just some pictures of engineers at work, and the one thing is, you do have a very diverse atmosphere. Say, for instance, this is a lab, so we have engineers in the lab looking at data. On a job site, we're usually in a construction trailer, so that's what this is. You're in a construction trailer working. This is working in the home office. This would be working in a plant. And so you do have a very wide variety of atmospheres you're working. So I think this is my last slide. Keys to success. Interpersonal and communication skills and teamwork. And that's true of any job you have, but this is probably one of the most important things that you need to realize when you get out of school and you go to work. I've seen a lot of young engineers go into our manufacturing plants and they, you know, they're feeling really good about themselves. They have this degree, they have a good job, they think they're, you know, smarter than a lot of other people, and they'll go into a plant to work on a problem, and they might not value the opinion of the hourly worker who's running that equipment, who's been running that equipment for 20 years, who knows that equipment like the back of his hand, and they go into a plant and they feel like they're going to be the knight in shining armor and figure everything out, but they don't talk to the people that have been working there every day, and they don't value their opinion. And that's one of the worst mistakes you can make, because, you know, everyone, especially those operators, they, like I said, they're there every day. They know that equipment. They might not know technically what's happening, but they know cause and effect, and they can be your best asset. And you have to treat everyone with respect. As an engineer, as a chemical engineer, process engineer in the field, in the food industry, a lot of our equipment is cleaned in place. So we have these very automated systems that clean equipment, and a lot of times cleaning is done on third shift, and it's done, a lot of times the cleaning crew that comes in, they're not usually highly educated. But you need to work with them, you need to treat them with respect, you need to dialogue with them, and as an engineer, like we talk to people that go from that span of the hourly worker, the cleaning guy, all the way up to the CEO. And so you have to be able to relate to that wide range of people. And most of the times you're working in a team, because you're working with controls engineers, you're working with plant staff, quality assurance, so you have to get along with people. And I've had engineers that have gone into a plant and they've not developed those interpersonal skills, and I've had the plant manager call me and saying, you know, your engineer is pissing everyone off in the plant, I don't want him back, you got to get him out, and I don't want him back. And so if every plant he goes to, I get a call from the plant manager because he doesn't get along with people, what's going to happen to that guy in 2 years? Is he going to have a job? No. So that's like one of the most important things. It's not even technical. And the other point is, engineers, we are very technical, and we think about things in a technical way. And when we're doing projects, we have to go ask for money. So it might cost, you know, you might be asking for $200,000. You might be asking for $200 million to build a new plant. And a lot of times you have to go through these reviews where people are asking you, what are you putting in, why do you need it? You have to be able to explain that in layman's terms. So that becomes very important. Problem solving and critical analysis. So I'm not going to read that list, but that's kind of what keys to success. When we're interviewing people, that's kind of what we look for, you know. Do you have a strong work ethic? Are you motivated? What experience do you have? So that's it, and we have 8 minutes left. It's not bad. So do you guys have any questions? Or I answered everything that you ever wanted to know about chemical engineering? No questions at all? Yes. 29 years.
What is the material skill of chemical engineering?
There's actually, you can get a degree as a materials engineer, and basically you're just studying, and you're just very knowledgeable about all the different materials that are available for use in commercial production. And you can, you know, like all the different plastics and concrete and steel, and so, you know, I don't know a lot about that field, but I do know that you can get a degree as a materials engineer, and then you're utilized in that fashion as an expert on materials.
What GPA do you recommend to enter the engineering field?
What GPA? As high as you can get. I mean, it really depends on the school, and you know, like when, are you talking about getting into college? Or,
so yeah.
Yeah?
Yeah.
Yeah, because I mean, they're looking at your SAT scores, they're looking at a lot of things, but the highest GPA you can get, the better off you are. And it's really, you know, not about the GPA, it's really about understanding the material.
What's been like your favorite project to work on since you've been an engineer?
My favorite project to work on.
Most memorable.
I don't know, I've worked on so many projects, I've forgotten half of the ones I've worked on. Probably, this goes back a while, but I worked on developing the Hugs and Hugs with Almond. And so that was a great project, because I got to work on that project from the very beginning to the very end. So when we built that plant, we put in our first white chocolate manufacturing process, the lines to manufacture those products. And this is kind of funny. This is how things work. Like we had a small piece of equipment that ran. We bought some equipment that ran 800 hugs a minute we could make off this production line. And we developed the process, and we actually made product that we use as to do consumer testing to get an idea of how does the consumer like the product. And then when we scaled it up and designed the full commercial scale process, those lines made like 12,000 kisses a minute, right? And so we're starting up these lines, and the first thing we do, it's made on those plastic molds, but we lay those chocolate stripes. I don't know if you're familiar with the Hugs product, but it's like the white chocolate that has the milk chocolate stripes on it and a chocolate center. And so we start this lineup and we start making it, and the first thing it does, it's supposed to put these chocolate stripes in the mold. Well, the stripes, and we wanted them to lay straight. Well, they wouldn't lay straight. They were like going all over the place. We're like, what the heck is going on? You know, it worked great when we had our small line. Well, here, the amount of, the velocity that chocolate was coming out of these little nozzles that are like 5 millimeters, they were developing a static charge, and they were repelling each other and going all over the place. And you know, we didn't figure that out at first, but what we do is these depositors that deposit the chocolate, you can like wheel them offline, and we would, you know, like, so if you're not running the line, the chocolate will set up and get fudgy, so you got to pull them off and you empty them out. And we'd have these metal carts that we put the chocolate in. And one day I walked by this cart, and I got like 2 inches from it, and the chocolate had so much static electricity, it arced and sparked me in the leg, shocked me in the leg. And then it's like, oh, okay. And so like these, you know, things that you can never think of happen. And that's what's cool about engineering. It's like, okay, well, how are we going to solve this? You know, here we are, we're under the gun, we're supposed to be making all this product, and, you know, marketing doesn't like it because the stripes are all over the place. And so that was an interesting project.
You said that people travel all around the world a lot.
Yeah.
How does that work? Do you have translators or?
A lot of people in other countries speak English. In China, yeah, we will have translators. Like we have 2 plants in Mexico, and a lot of the professional staff are bilingual, but all the operators, most of them don't speak Spanish. So if you're there for a long period of time, we'll hire a translator, and we'll work with a translator. In China, we work with a translator. But everywhere else, like most European countries, they all speak English. And it's pretty good English.
How far into calc will you go?
I'm trying to think if there was anything past differential equations. So like you do all your calculus, and then you do differential equations, you do linear algebra, and then you start getting into things like, we had to take a process controls course, and that math was really abstract. I mean, that was like beyond differential equations, but it was all applied to process controls. It's a lot of math. It's very abstract. It's not fun. Oh yeah. Any other questions? How are we doing on time? 9:58, 9:59. I guess you guys probably go to your next session. Thanks.